Hello and welcome to my presentation on our work towards a privacy-preserving marketplace for air traffic flow management slots. My name is Christoph Schütz from the Johannes Kepler University Linz, and I'm presenting on behalf of the Slot Machine Consortium, which is composed of the Austrian Institute of Technology, Swiss International Airlines, Eurocontrol, Frequentis, and of course the Johannes Kepler University in Linz in Austria. As I said, I'm going to present our preliminary results towards a privacy-preserving marketplace for ATFM slots. This work is carried out as part of the Slot Machine project, which is currently running until the end of 2022. I'm going to present the problem that we face, that we're trying to solve, and also preliminary results and solutions that we intend to apply in this project. In the Slot Machine project, we're trying to solve the flight prioritization problem. What is this flight prioritization problem? So the idea is that in case of a regulation, so in case that there's a congestion at an airport, airlines are faced with costs, of course. So every delay of a flight is associated with costs. How high these costs are, so the amount of the costs, really depends on the flight. And typically, those flights have non-linear cost functions. So non-linear cost functions in case they are delayed. So typically what you have is you have one or more delay targets for each flight. And if the delay target, or if one delay target is missed, then there's a significant rise in the costs for this flight. For instance, a flight may have some work-related restrictions for the flight crew. So if some delay target is missed, then the flight crew needs to be replaced. And this, of course, results into, well, considerable costs. Now, the idea is that we leverage the fact that flights have usually different cost functions. So for some flights, as you see here, flight C, for instance, on the left-hand side, there's a comparatively long time till the first delay target. So flight C has only a moderate rise in costs at first and can wait for a little bit longer with respect to the departure time that you see here as a dashed line. Flight B, on the other hand, in this example, has a very steep cost function already at the beginning. So the delay target is very early and associated with a considerable rise in the costs. Whereas flight A is a little bit in the middle between flight B and flight C, so it could wait longer with respect to the point in time that's represented by the dashed line. So now let's assume that we have these three flights with these different cost structures, and then in case of a delay, in case of a congestion, there is a new departure time. Flight A is assigned to start first, so it's assigned the first slot. Flight C the second, flight B the third. But of course, if we look at the cost function, what we see is that the global optimum would be different because, of course, flight C could wait the longest of those, whereas flight B should depart very early, and also flight A could wait a little longer. So what we could do is basically swap flight A and flight B. So we assign flight B the first slot, and then flight A can again swap with flight C. So because flight C can wait the longest, and then we have a different departure sequence. So we would have flight B before flight A before flight C. So that, from an economic point of view, would be the global optimum with respect to the total costs incurred by all the flights together. But of course, in order to realize such optimization sessions, we need the appropriate system for this. And that's where the slot machine project comes into play. So what we are currently doing in the slot machine project is that we developed a slot machine system, which consists of basically a heuristic optimizer and a privacy engine. And the idea is that airspace users communicate their preferences to the slot machine, which employs an optimization algorithm to determine an optimal slot sequence. The special thing about slot machine is that we have the privacy engine, which employs secure multi-party computation in order to keep the preferences submitted by the airspace users private. Not even the slot machine is able to read the plain preferences, the unencrypted preferences submitted by the airspace users. So those preferences remain secret even to the slot machine, so that the data, the confident data by the airspace users, remain private. We're also working towards a flexible credit system, which is also an idea put forward by the UDPP mechanism, so by a user-driven prioritization process, which was developed by Eurocontrol. And we will employ blockchain technology to make the process transparent, and also to keep track of the flexible credits that are collected or that are obtained by the airspace users through participation in the slot machine project. Okay, so let's look a little bit more on the technical aspects. So let's characterize the problem a little bit more into detail. So what we basically have is a flight list or a flight sequence. So we have flights which are assigned a slot, a departure slot. So originally a flight has, of course, an ID, which uniquely identifies the flight, but it also has an original scheduled time. So, for instance, here we have the Swiss Air flight 243, which originally was scheduled at 10. In case of a regulation, is then assigned a new slot, a new departure slot, which is characterized by the time 1430, for instance. So, to characterize this problem a little bit more precisely, so what we have is that a slot may be assigned to at most one flight, and a flight is assigned to exactly one slot. Now, the flight prioritization problem then boils down to query ordering. So we have a sequence of flights. If you look on the bottom of the slide, we have the sequence A, B, C, D, E, F. And then based on some additional preferences submitted by the airlines, we could determine, for instance, that the ideal flight list is indeed BCA FDE. Now the question is, of course, how do you specify, how do airlines, airspace users specify their preferences for the different flights? One proposition would be to use margins. And here it's important to say that those specified margins are not hard constraints. So the violation of those margins does not invalidate the solution. But those margins are used to determine the preferences of the airlines. So for instance, we could have one proposal put forward by our colleagues from Swiss would be to use a simple model where we have a time wished, where we have a time not before and a time not after. So ideally, a flight should be assigned a departure time close to the time wished. It should definitely not be earlier than the time not before and not later than the time not after. So after that, after the time, if a flight departs after time not after, then what the airline would say is that here we have a significant increase in costs. Then also for each flight we could specify whether it's high priority or not, or if a Boolean value is not enough, we could also assign an integer number to indicate a priority value for each flight. Now, in order to simplify the optimization process and for our first experiments, what we do is we derive a weight for each flight, a weight map for each flight. So we have one weight for each slot, flight and slot, which indicates how preferable a certain slot would be for a certain flight. And this weight is then kept secret. So it's encrypted. It's not visible to the slot machine or to any other party. And we could, for instance, use a nonlinear function to derive the weight from the margins, time not before, time wished, and time not after. This function could be configured by airlines, so really every airline could use a different derivation rule. But one possibility would be to assign the highest weight to the time wished slot for each flight, as you see on the right-hand side on this curve here. So the time wished for a slot and flight. So what you see on the right-hand side is how the weights for one flight are distributed over the set of slots, of available time slots. So the highest score, the highest weight for this flight would be assigned to the time wished slot, or those slots closest to the time wished. And what we see here is that every slot after time not after is then assigned a weight of 0. We could also have gradually decreasing weights after time not after, as we see it here in time not before. So really we can have different weight derivation functions. But the important thing is that we have here this non-linear component as well, as we seen early on as well. So we have, of course, time wished as the most preferable slot, but then it linearly decreases till time not after, and then we have a sudden drop in the weight, which means that everything after time not after is really undesirable for this particular flight. Okay, then for the different flights, we have the weights for each slot, and then we can use these weights to calculate a fitness value for each solution. So on the bottom, you see example solutions, example flight lists or flight sequences, along with a fitness value that is computed based on the weight map that you see here. So for instance, on the left-hand side, the solution, we have a fitness value of 190, which derives from the fact that B associates a weight of 0 for the first slot, C associates a value of 20 for the second slot, A associates a value of 100 for the third slot, and then F and D associate a value of 0 each for slots 4 and 5 respectively, and flight E associates a value of 70 with the slot E, and when you sum up those weights, we get a fitness value of 190. And so what we can use this fitness value then to rank solutions accordingly, according to the preferences of the different airspace users. So how does optimization in the slot machine project then work? So we use a heuristic optimizer, heuristic optimization algorithm, to find different solutions to the flight prioritization problem. We evaluate the flight list, so each solution is evaluated in a privacy-preserving manner using the privacy engine, which again uses multi-party computation nodes to carry out the computation of the fitness value in private. We could use different meta-heuristics to find the flight list. So we could use genetic algorithms, which was our original first choice, but we could also use taboo search, simulated annealing, hill climbing, which in our first experiments tended to yield slightly better results. Okay, so let's look at the principle again. So the heuristic optimizer looks for different flight lists, solutions to the prioritization problems. The privacy engine then is used to evaluate the fitness, evaluate the flight list, and return a fitness value to the heuristic optimizer. And as I said, the privacy engine uses multi-party computation over the secret weights, so which are not deciphered by the slot machine system, but are actually not known to the system itself, but also not known to other parties. And then based on those fitness values returned by the privacy engine, the heuristic optimizer chooses how to further adapt the previous solution, and then the privacy engine is called again with a different set of solutions. And so iteratively, the solution, the flight list, is improved. So now, if you are familiar with solving optimization problems, then you might ask yourself why we chose a heuristic search function instead of a deterministic algorithm such as the Hungarian method. The idea here is that we want to separate the search for solutions for the flight prioritization problems from the evaluation of the solution, because the evaluation should be carried out by the privacy engine, and in order to be able to carry out the computations in a privacy-preserving manner. And also, the system should be able to parallelize the search